So 4.3 was about rational functions, which basically were functions you could write as fractions. 4.4 is on radical functions. See my font there? It's radical font. It's pretty cool, huh? Yeah, I know. So radical functions. So radical functions are functions that have roots in them, like square roots, cube roots, things like that. The two main things that we do with radical functions, we graph them, and then we're going to solve some equations. So it's one section, but we'll just get as far as we get today, and then we'll just finish it tomorrow, and then Thursday will be review day. All right, so that's some examples of radical functions. The first one, this is a square root function, the square root radical. That's a cube root radical. Generally, if you're taking a square root, you don't put a number in that spot. You just leave it blank. If you're taking a root for anything other than a square root, like a cube root or a fourth root, you need to put a number in that spot. Let me show you on the calculator how you can do roots. Well, for square root, there's a button. So if you wanted to take like the square root of 16, you just press second, x squared, and you do 16. If you want to do a cube root, you can press math, and the fourth option down is a cube root. So you press 4, and that's how you do a cube root. We could do like the cube root of 27, and you get 30. Now, if you want to do something higher than a cube root, there is no button for doing it. So let's say you wanted to do like a fifth root. The only way to do a fifth root is you type in the number for the root you want to do. So 5, that's a fifth root. Then you press math, and you press the fifth option down. What the fifth option does is it takes whatever number you typed in before it, and it puts that number in the root. So you could do the fifth root of 32, and you get 2. If you want to do a 12th root, you'd have to type in 12, math, and then press option 5. And that's how you do a 12th root. Okay, so square root, cube root, you've got buttons for. Anything else, you have to use option 5. Any questions on typing that in? Okay. So basically, any expression, okay, this one's a little simpler, it just has just a single root. Any expression of the form that has that symbol and then a number right there that's greater than 1. If it's 2, it's invisible. You don't have to write it. Okay, like this one. Is called a radical. So this is a radical. Cube root of 24. That's a radical. Square root of 13. The number that you put right there, which in that case it's a 3. In this case it's not written, but it's what number there? 2. Yeah, it's a 2. If it's ever not written, it's always a 2. That's called the index. So the number that you put outside is called the index. In that case right there, it's a 5. And the thing that's underneath the symbol, that is called the radicand. So in this case, the radicand is 24. In the one next to it, the radicand is 13. Okay, so the number on the outside is called the index. What's underneath it is called the radicand. And that symbol, that's just called the radical sign. Whether it's a square root radical sign or a cube root radical sign, that part doesn't really matter. little bit of vocabulary just to kind of start off. Any questions on any of those words? Radical, index, radicand, or radical sign? All right. I already told that to you. If there is no index written down, you always assume that it is a 2. It's a 2. Now, let me show you something. Let me type in the square root of 25. Okay, what am I going to get when I hit enter?
5.
Yep, I get 5. Now I'm going to take 25 and I'm going to raise it to the 1/2 power. And I hit enter. I get 5. Let's try another. Let's try the square root of 49. What do you get?
7.
Get 7. I'm going to take 49 and I'm going to raise it to the 1/2 power. What do you think I'll get when I do that?
7.
Yeah, I'll get 7. So if you want to write a square root symbol, but let's say like you didn't have the square root symbol, or for some reason you don't want to use the symbol, but you'd rather use an exponent instead, you can. Right? So there's a way to write square roots with an exponent. And the way to do that for a square root is to use the 1/2 power. Raising something to the 1/2 power is exactly the same as taking the square root. How about if I wanted to do a cube root? Does anybody have a guess what power I could use instead of the cube root symbol?
1/3. Oh,
Yeah.
sorry.
You could do 1/3. Sorry.
That's a good power.
How about if I wanted to do like a 4th root?
1/4.
1/4. It's always 1 over the number that you see right there. That's exactly the same as a root. So if you ever forget how to do a cube root, but you remember it's the same as a 1/3 power, you could do like 27 raised to the 1/3 power. You get 3. It's exactly the same thing as a cube root. All right, let's try this one. This is a 5th root. So what would be the same thing as a 5th root?
Just 1/5.
What is it?
The exponent of 1/5.
Yeah, you just put an exponent of 1/5. It doesn't matter. It doesn't matter what's inside here. We're just getting rid of that root symbol. So the 5th root is the same as a 1/5 power. Now, this, in math, that's a power raised to a power. Does anyone remember what you do when you have a power raised to another power?
You add them together.
That's if you're multiplying like things with the same base.
Okay. And you are multiplying the base parentheses.
So that would be like x to the 7. That plate there, you add them. Other guess what you do?
You multiply them.
You multiply them, yeah. What's 1/5 times 4?
4/5.
4/5, yeah. So this is exactly the same as that. So it just gives you a way to write something without the radicals. And this one happens to simplify a little bit more than the other ones. Any question on that? All right. So what does it mean? You might see directions in the book that say solve the following problem for the principal root. Well, we know when we do roots, like a square root, how many answers do we have? Like if I said, what's the square root of 16?
1. Usually 2.
2. What would be the square root of 16?
4 or negative 4?
4 or negative 4. When they specifically say this, they want 1/8. So if you're dealing with an odd index, you're basically solving this equation. Right? So this is how I would explain to somebody how to do a root. Right? Let me show you an example. Let's say I wanted you to do the cube root of, let's do 125. And somebody said, I don't understand what that means. Like what does that mean? How do you find the cube root of a number? I'd say, okay, that means, can you think of a number that you can raise to the third power and the answer comes out to 125? That's what this means. Yeah, it would be 5. So if somebody doesn't understand what the cube root of 125 means, I think of it like this. There's something that you can raise to the third power that gives you 125. And the answer is 5. Right? So that's what I mean by you're basically solving an equation just like that. So that's for an odd number. Now, if this is an even number, we have to be careful. Because if it's even, what happens if you try to take the square root of a negative number? Yeah, what do you get? What kind of number would you get? You get an imaginary. So first of all, when we deal with even roots, we have to make sure that whatever is underneath the root, this thing, we have to make sure that that's a positive. Well, we have to make sure that it's not negative. Say it that way. So with even roots, you've got to make sure that what's under the root is not negative, because we're not dealing with imaginaries. You're basically solving the same type of equation. So we're looking for an answer that is not negative. I think I got a couple examples. I'll make one up. All right, let's say find the cube root of 34. So if I ask you to explain what that really means, how would you think of that as an equation? Like if you wanted to reword that and explain it to someone differently.
X to the third equals 34.
Right. It means that there's something you can raise to the third power to get 34. And the way you would solve that, how do you get rid of cubing something? What's the opposite of?
You square root them, or you root them.
Yeah, what root would you have to take to undo cubing?
The cube root.
You take the cube root. So you end up taking the cube root of each side. Cube root and cube cancels. And here's your answer, the cube root of 34.
That's what we started.
Yeah, that's exactly what you started with. So you get about 3.24. Alright. So what you might see is something like what's on the right-hand side to start. X cubed equals 110. If you had to solve that, how would you get rid of cubing and get x by itself?
Cube root.
Yeah, take the cube root. Take the cube root. Take the cube root. Cube root and cube cancel. And now you just need to use your calculator and find the cube root of 110. Okay, which is about 4.79. How about if I had x to the fourth equals 28. What would we have to do to get rid of the power of 4?
Yeah, like square root to the fourth, like the fourth square root or something. I don't know how to say it right correctly. Yeah, it's just take the fourth root.
Take the fourth root.
I'm trying to get the words and I couldn't get them.
Yeah. Take the fourth root of both sides. Now, what kind of root is that? Is that even or odd?
Even.
That's even. When we do an even root, we have to make sure that whatever we're taking the root of is bigger, greater than or equal to 0. Is 28 greater than or equal to 0? Yeah, and that's going to work fine. So type in 4, math, option 5, 28, and you get about 2.3, roughly.
What does that symbol mean? Like that squiggly?
Means it's about 2.3.
About?
Yeah, it's not exactly 2.3. I rounded it off. Right, so a big thing just to be careful, if you're doing an even root, make sure that you're not having a negative number under it. Okay? And the answer that you get is always going to be non-negative. Just like that number, 2.3. That's a non-negative number. Any questions on that? All right, let's look at this one. So we're going to take some square roots and see if when you take a square root, it gets bigger or smaller. See what I did with the font there too? Yeah. So smaller, it's smaller, and larger, it's like larger. Yeah. There you go. All right. Let's try 4. When you take the square root of 4, what happens? It gets smaller. What do you get? 2. You get 2. So when we took the square root, it got smaller. Okay. Let's try this one. The square root of 18 is about 4.2. Did it get smaller or larger? Smaller. That's smaller. So it looks like when you take the square root, it gets smaller, right? Mm-hmm. Okay. What's the square root of 1?
1.
1. Did that one get smaller?
No.
No. All right. So maybe when you take the square root, it either stays the same or it gets smaller. Let's try this one. 0.5. So the square root of 0.5 is 0.71. What happened that time?
You got bigger.
Yeah, it got larger.
Close to 0 larger.
And if you take the square root of 0.2, you think it's going to be smaller or larger?
Larger.
Yeah, it's going to be larger. Came out to about 0.44. So whether or not you take a square root and it gets smaller or bigger depends on the number. When do you think it gets smaller? If you take the square root of,
anything greater than 1.
Anything greater than 1. When do you think it gets bigger?
Anything less than 1.
Anything less than 1 and greater than 0, because we can't go negative. Anything between 0 and 1, it gets bigger. And when did it stay exactly the same?
1.
When you took the square root of 1. Okay, so whether it gets smaller or larger, well, it depends. Okay, any question on that? All right. So let's look at a graph of a square root. All right, let's do 2 different roots. Let's do square root of x, and then let's also do 4th root of x. They're both going to look pretty similar. All even roots kind of look the same. 4th root, 6th root, 8th root, they look the same. Let's grab a square root and a 4th root. And we'll do zoom 6. So there's your square root. There's your 4th root. Now, if you look at those roots, they're both in what quadrant?
First quadrant.
They're both in the first quadrant. So let's forget about looking at 2, 3, and 4. And let's just zoom in on quadrant 1. So let's go 0 and 0. Okay, so there's a square root. And there's a fourth root. Let me make that a little bigger. Does anybody notice anything about that picture? Yeah.
The red starts out greater than blue.
Right. But then it ends up
And then lower.
lower. So this ties in with this idea. Whether a square root, is it larger or is it smaller? Well, that basically means, is it above or is it below? Where'd that graph go? There it is. At 1, they're exactly equal. But after 1, one of them is under. Before 1, that one is above. So 1 is an important number when we're doing even roots. Okay? It's kind of where the roots change places. If I add in a 6th root, let's see what that looks like. So take a 6th root of x. 6 math 5x. I'm also going to set my y max a little lower because I don't need it as high as I have it. Oh, that was x max, wasn't it? Oh, that's fine too. Right, so there's your square root. There's your 4th root. Takes a while. And here's your 6th root. Anyone starting to notice anything else about all of these graphs?
The bigger the root, the more it is before the blue, and then it gets lower.
Yeah, so the higher the index, the lower it is as you get past 1, but the higher it is as you get before 1. How about anything else about all these graphs? What do they all do something.
They all intersect at 1.
Yeah, they all intersect at 1, 1. They also all go through another point. It's a little harder to see just because of the way the calculator does it.
0.
Yeah, they all start at the origin. Yeah. Right. So these are all different properties of even roots. They all go through the origin, and they all cross at 1, 1. Let's look at the domain of that. Remember, that's just quadrant 1. It didn't go in any other quadrant. What's the domain of all of those graphs?
0 to infinity.
0 to infinity. Yeah. Domain is 0 to infinity on all of them. They all start at the origin, and they all head to the right forever. How about the range? What's the lowest they go, and what's the highest they go?
0 and 10.
And the highest?
Infinity.
Infinity, right? This blue one, all of them are going to keep going up. The black one, it almost looks like it's getting flat, but it's still going to keep going up. It just goes up very slow, but it will keep going up forever. So for even roots, the domain and the range is restricted to 0 to infinity. All right, now, what if I took, just graph square root. What if I put plus 2? What do you think that plus 2 is going to do? Yeah?
Can move it up to.
Yeah, it's going to move it up 2. So now, instead of the graph starting at 0, 0, it starts at 0, 2. Does that affect the domain, shifting it up 2?
No, you're still starting at the origin.
I'm still starting at the origin and going to the right forever. Did it affect the range?
Yes.
Yes, it did. What's the lowest that it goes now?
2.
2. Yeah. So the domain and range is 0 to infinity if you don't change it. But if you change it, then you have to adjust for that. Okay. Any questions on that was it there? Those two properties. Okay, so those are for even roots. Let's graph an odd root. So let's put in the cube root of x. So math, option 4. And I'm going to do a zoom 6. Tell me what you notice right away that looks very different about a cube root compared to an odd root. Okay, so what's different?
It kind of like switches, like the last one, it kind of just went in one direction.
The last one went in one direction. How many directions does this one go in? 2. Goes in 2. So with a cube root,
It reflects both of the y and x axis.
yeah, it's like a mirror image. I call this point right here the center point.
So it flips over the origin.
Yeah, it is a reflection over the origin. Yep. Which means it's a reflection over the x and the y at the same time. So this is called a center point. When we talk about roots like this, I call this a start point because it starts here and it goes one way. Yeah.
So do we call that an end behavior model?
No, there is no end behavior model for this because this is not a rational function. This is a radical function. So those ideas, they don't apply to these kind of things.
It looks a lot like the cubic root.
Yeah, it's kind of like a cubic. Now let's graph a fifth root and see if you can maybe see some patterns here. Yeah, I'm gonna zoom in a little bit because it's kind of hard to see. So let's do zoom in. I'm gonna zoom in right at the origin. Okay, so there's your cube root. It is connected, even though it looks like it kind of does something a little funny. It's connected. Okay, so that's a cube root and a fifth root. Anybody think they see a point that both of them go through?
1 and -1.
1, -1?
1 and 1 and a -1 and -1.
Okay, yeah, so 1, 1, definitely. -1, -1. Yep.
0, 0.
And 0, 0. It's hard to see that, but yeah, they both go through 0, 0. So with odd roots, they share those 3 points. Even roots share 2 points. Okay, and let's look at the domain and the range. How far left and right does it look like those graphs are going to go?
Negative infinity to infinity.
Yeah, they're going to go left and right forever. How about up and down?
Same thing.
Same thing. So when you're dealing with odd roots, the domain and the range are both all real numbers. So what that means is if you're dealing with like a cube root, you can take the cube root of any number you want. Positive, negative, doesn't matter. Even roots, that's not true. If you try to do negatives, you're going to get imaginary answers. That won't happen with odd roots. Right. Any questions on how those graphs share those 3 points, or why the domain and range is all real numbers? All right, so last thing we'll look at, which we've done before with other functions, are the transformations. So with transformations, there's always 2. One of them is a shift left and right. Another one is a shift up and down. One is a stretch horizontal, and then one is a stretch vertical. So the transformations are going to work very, very similar to everything we've done before. And now let's look. Does anybody remember what A usually does? That's adding or subtracting a number inside the function. So in this case, inside means under the root. Yeah?
Horizontal shift.
Yep. And what I'll do is, you know what? I'm going to put this so we have a little more space. I'm going to put it over here. C times the root of bx plus A plus t. So yeah, A is a horizontal shift. What if it's a plus? Which way does it move it? Left, it's backwards. And if it's a minus, it would move it right. Okay, so that's A. Let's look at B. Is B still under the root? Yes, then it's still something horizontally, but it's not a shift. What's the other kind of transformation we did?
Horizontal stretch.
It could be a horizontal stretch or compress. Depends on the number. If it's bigger than 1, what do you think that's going to cause the graph to do? Be careful because it's horizontal. Big number is going to make the graph compress. Yes. The bigger you make B, the more compressed you make the graph. What about a small number like 0.5 or 0.4? What do you think that'll do?
It's going to stretch it.
Stretch it. Okay, so that's B. And that covers the horizontal stuff. Okay, C. Well, C is multiplication, but this time it's outside the root. So anyone have a guess what that's going to do? Yep.
Vertical stretch or vertical compress.
Yep. Could be a stretch or compress. How about this time if your number is bigger than 1?
Vertical shift. Oh, that's stretch.
That is going to stretch. The vertical stuff isn't backwards. It's what you would expect. Big numbers make it stretch bigger. Small numbers compress it smaller. So press. And D. That's the only one we didn't do.
For horizontal. So that's less than compresses and then greater than 1 stretch, or is it the other way around?
Nope, that's correct.
Okay.
Bigger numbers make the graph smaller when you do horizontal.
Okay.
Yep.
How would you do this?
So a horizontal stretch or compression would look like this. This is a horizontal compress. That's the normal one. That's a horizontal compression, like that.
Yep.
That's a horizontal stretch, like that. Vertical compression, like that. Vertical stretch, like that. All right. So what do you think D does? That's adding and subtracting a number, but it's on the outside. So it's like A, but it's outside instead of inside.
Vertical shift.
That's a vertical shift. Yep. Vertical shift. And which way do you think positive would move it? Up. And a negative? Down. What if B or C was a negative? Does anybody remember what that causes the graph to do?
Reflect.
Yep, causes it to reflect. If B is negative, it would reflect horizontally. A horizontal reflection would look like this. Left to right. And if C was negative, that's a vertical reflection. That would look like this. Up to down. All right, so we'll just finish up by explaining the transformations here. Most of them just have one, so they're pretty quick. See if I can keep this on the board at the same time. That -2. Which letter is that up at the top there?
A.
That's A. And is it a positive or a negative? It's a negative. So what's that -2 going to do to the graph?
It's gonna make it go
how many units?
2.
Yep. So shift right 2. That's that one. How about h of x?
Shift left 3.
That's a shift left 3. Now, this one isn't quite written the way we normally would write it. What's backwards about the 3 minus x?
Reflection over an axis.
And how should we normally write this?
X minus. Or it should be X plus. X.
Negative x plus 3.
Right, you should think of it as negative x plus 3. So and you follow the order that I wrote the letters. It has to be A, B, C, then D. So what's the first thing that's happening there? Well, the reflection is letter B, but there's something on letter A we have to write first.
Go horizontal shift left.
So we have to shift left 3. So shift left 3. And then the negative, it's like having a negative 1 right there. What's the negative 1 do?
Horizontal compressed by negative 1.
Horizontal reflection.
Just a reflection, yeah.
Just a reflection.
There's no compression there because that number is a 1. So the 1 doesn't change anything. The negative causes it to flip. It's a horizontal reflection. Yeah.
What axis is the horizontal reflection reflecting on?
A horizontal reflection is reflecting over the y-axis. This would be horizontal. Something like that's a horizontal reflection. So that's on the y-axis. All right, so we can try another one of those tomorrow if we want, and then we'll get into some sketching and solving equations. So we only have like 4 slides left, so plenty of time to finish. Let me adjust that. So 255. Let's see. Actually, I want to really change this a lot. So. Let's do 5 through. Yeah, that's it. We'll just do 5, 6, 7, 8, and 9. Okay, it's all describing transformations. So 5, 6, 7, 8, 9.
That seems awfully simple.
Yeah, it's a pretty simple.
That's
Don't get them